So let's look more closely at electroplating. Remember that this was applying a thin layer of another metal, generally a low reactive metal, onto an object. So, another main difference with electrolysis compared to electrochemical cells is we've only got one container now. Before we had two beakers and we had to join them with the salt bridge. Now everything's happening in the one container. So here is my anode. And like I pointed out to some of you in marking your assignments, when we're labeling it, we're going to point to the thing. Okay, that's the anode, the actual metal bit that is being poked into the solution. Now, I'm not quite sure how to draw a teapot. It's going to look pretty. I've got to have a hand. Okay, so this is my teapot. Sort of looks like a strange elephant, but anyway. This is the cathode. And because I want to silver plate this teapot, my anode is going to be made of silver. I'm also going to make sure that my electrolyte, which is a solution that can conduct, is going to make sense to make it silver nitrate. So we've got silver ions already present, as well as the ones that will come off our anode, and we'll also have silver ions that will reduce onto our cathode. Now, instead of having a voltmeter, we need to have a power supply. And this is a battery. This represents a cell. So a battery is a series of cells. So yeah, Americans are correct when they call their phones cell phones, because it's not a battery in there, it's a cell. But your car battery is a battery, it's got 6 cells. Anyway, that's sort of beside the point. But the important thing is here that the long stick is positive and the short stick is negative. We have to get our charges around the right way. How I remember that the long stick is positive is that this is only a short stick for negative. But if I write the positive symbol, I've got 2 short sticks, and if I added them up, I'd end up with a longer stick. Yeah? Now you might notice that my positive terminal is now on my anode side. Okay, so this is positive and this is negative end, which means that my anode has a positive charge and my cathode has a negative charge. Right? So this is important to note the sign change. But the reason why we've done this is so that we can continue to say that for all of our electrochemistry, oxidation occurs at the anode. Right? So that rule applies to everything. So that's our rule, but our sign changes with electrolysis. Okay, so now if we look at what's happening on page 9, we know that our anode is getting used up in this reaction, and that we are coating the object here for our cathode. And the only requirement here is that it must be able to conduct. Okay, so because we're going to be putting a layer over the top of it, it doesn't matter what it was, as long as it conducts. So what are our reactions? Well, our oxidation reaction, Ag plus, Ag solid is to Ag plus. What's our reduction reaction? What's happening at the cathode?
Opposite of that.
The opposite of this. That's exactly right. So this is for electroplating. Our reactions will get a little bit more complicated than this as we progress. So how much charge are we going to need to add for this reaction to occur? If I look at my electrochemical series, I know that I can just copy straight down for the reduction half here, which would be plus 0.80 volts. Is that right? Does everyone agree that? Yeah. What about this one for the oxidation? What value is that going to be? Negative 0.8. So what happens when I add these up? I get 0. That calculation is actually correct, but common sense would tell us that the reaction won't happen if we don't actually apply a voltage. So this means that this reaction will occur with a very small voltage, minimal voltage. And if we had too great a voltage, if we just sort of cranked it up, say, oh well, we want to get through electroplating, hundreds of teapots today, so let's crank it up and zap these teapots with as much as electrical energy as we can. That won't work, because what happens is that we'll still be reducing those silver ions, but they won't stick very well to the teapot, and you might end up with a silver depositing not on the teapot, or it could be in lumps on the teapot that easily break off. And so electroplating is done over a long time at a very low voltage to make sure that it sticks well to the product that you have at the cathode. Any questions so far?
Does that mean only one thing can be electroplated at a time?
Well, as long as it has a negative charge, you could put in more things. Yeah. So if you had a really big vat, you could put in lots of teapots. As long as they've all got a negative charge and it's a low current, then you could do more than one at a time.
Could you put in extra anodes, or does it have to be an anode?
Well, it would depend on the setup, really. That would be more an industrial sort of question that might vary according to the applications. But we know that this is getting used up over time. And so the more teapots that we have in, the more we'd have to think about, well, if we got enough silver ions available for this reaction to occur. You can also top up your solution, though, because really, when you switch this on, the moment you turn it on, it's the silver ions in solution that are going to be reduced onto the teapot first. And then the anode is going to be topping up the solution really. Yeah, so there are ways around it. Obviously, it would be quite inefficient to have just one teapot in there at a time, kind of thing. But you need to make sure it's a balanced system. Any other comments? If we look at the next example, which is on page 11, we've got corrosion protection. And so this carries on from what we were talking about last week with our tin can. And yes, tin cans are not protected in the same way as this diagram would indicate, in that we don't put in an open can. This is just an illustration. So if we've got, and when we're drawing our diagrams, we need to draw it the same way every time, where this is the anode on the left. Now sometimes some diagrams in tests and exams will be reversed to try and trick you and have the cathode on the left, but when you are drawing one, the convention is that you will draw the anode on the left. And we're going to be tin plating this tin can. So my anode will be made of tin. I want to have tin ions in solution as well. So I'm going to start out with a solution of tin nitrate. What's my can made of?
Iron.
Yeah, so we'll call it a steel can, which means that it's iron. And this then is my cathode. What are my charges? Because this is electrolysis. What charge do I put on my anode? Positive. And I've got a negative charge then on my cathode. I must have a power supply, or it won't work. The other way of representing this is I could just write power supply. If I do that though, I still must write the charges on the sides to show that I know that my anode has to be connected up to the positive terminal for power supply. Okay, so here what we want to do is quite similar to our electroplating. Our oxidation reaction. What's our reduction reaction? The opposite. So what can you tell me about the voltage that's going to be required? If I looked up tin, or the tin-half equation for reduction, negative 0.14 volts, what's oxidation going to be? Yeah, just positive. When I add them together, 0 volts, because it's the same. Okay, we're still applying a coating over our steel here. The idea being that we can protect the contents, we can protect the can from rusting in contact with acidic food, etc. And in reality, cans are made, like the metal is rolled out flat and then rolled into cans. It's not sort of made up as a can first. but we can do this with minimal voltage again. Now, because this is negatively charged, our positive ions are attracted over to the cathode. But our nitrate ions with a negative charge are also attracted towards the anode. Okay, the opposite charge will be attracted to the electrodes in electrochemical cells and electrolytic cells. Yeah, because it's simply that opposite charges will attract in all environments. And like charges will be repelled. Okay? And let's just get you to work on questions 1 to 3 on page 12.